Significant figures. Objective: to learn to identify the significant digits in the value of a measurement.
We come across many measurements in our daily life. A measurement is expressed in the form of a real number. Suppose we have expressed length of a piece of wood as 43.65 centimeters. Here, we have used a meter scale with centimeter as the smallest division to arrive at this number. Least count of the scale used is 1 centimeter. With the help of the naked eye, we can approximate the length up to 1/10 of a centimeter, which is millimeter. Accuracy beyond millimeter is not possible. The reading is certain until 43 centimeters. The digit 6 is not certain, but can be considered reliable. The certain digits along with the first uncertain digits are known as significant digits or significant figures. The digits 4, 3, 6 are significant digits, and the digit 5 is insignificant. The number of significant digits in a measurement depends on the precision of the instrument. Thus, the measured value must be reported in such a way that it indicates the precision of the instrument used for measurement. In other words, it must be an appropriate number of significant figures. It is common in scientific communication that values of various measurements are given without specifying the precision of the instrument used to arrive at the number. Hence, some rules are framed to identify the significant digits in the given value of a measurement. All non-zero digits are significant. For example, 423 has 3 significant figures. 172.38 has 5. And 5.1 has 2 significant figures. All the zeros between two non-zero digits are significant. For example, 306 has 3 significant figures. 240.6 has 4 significant figures. And 60,001 has 5 significant figures. In the numbers less than 1, the zeros on the right of decimal point but to the left of the first non-zero digit are non-significant. The underlined zeros in these values are non-significant. So, 0.004 has 1 and 0.009015 has 4 significant figures. The zeros at the trailing end of a number without a decimal point are not significant. Thus, the number 2020 has 3 and 45,000 has 2 significant figures. The trailing zeros in a number with a decimal point are significant. For example, the underlined zeros are significant. Thus, 7.400 has 4 significant figures and 0.906200 has 6 significant figures. Now that we have understood how to count the number of significant digits in a number, let us see if the significant figures are constants when the value is transformed into different units. The mass of a sample in a laboratory was measured to be 50.400 grams. The value has 5 significant figures. In the unit of a higher order, it is equivalent to 0.050400 kilograms, which also has 5 significant figures. In the unit of a lower order, it is equivalent to 50,400 milligrams, which has 3 significant figures as opposed to 5 in the actual measured value. When there is a need to change the units of the reported value, the number of significant figures must not change. To remove ambiguities in determining the significant figures, scientific notation is a better way of reporting the measurements. The scientific notations are expressed as A into 10 power B, where A is a number between 1 and 10 and B is an exponent or power of 10, also called as the order of magnitude. The exponent is irrelevant to the determination of significant figures. And number of significant figures in A becomes the number of significant figures in the measured value. The value of 50.400 grams in scientific notation is written as 5.0400 into 10 power 1 grams. In lower order, this is 5.0400 into 10 power 4 milligrams. In higher order, this is 5.0400 into 10 power minus 2 kilograms. We can see that the number of significant figures in all 3 cases remains the same. This way of notation keeps the information about significant digits intact while changing its units.